Hello, everyone, and welcome to our today's Quanser user webinar. We invited Dr. Steven Mascaro from the University of Utah to talk about the robot control course he developed. My name is Zuzana Fabushova, and together with my colleague Pasha Javid, we will be your hosts and webinar moderators today. And now I will pass the microphone to Pasha to introduce our today's presenter.
Thank you very much, Susanna, and hello, everybody. Good morning or good afternoon, depending on your time zone. Thank you very much for joining us today. First, I'd like to begin by saying that we hope that you are all doing great, fine, healthy, and safe. Yourselves, families, friends, students, colleagues, wherever you are, we hope that you're keeping safe. We really appreciate the chance to remain connected to you. My name is Pasha, and along with my colleague Zuzana, we will be hosting the webinar. But I have been given the pleasure and the honor of introducing our speaker today, Dr. Steven Mascaro, who, as mentioned by Zuzana, is currently an associate professor in the Department of Mechanical Engineering at the University of Utah, as well as the director of the Biorobotics Lab. His main research and teaching interests are primarily focused on robotics and mechatronics. He received his bachelor in mechanical engineering from Clarkson University, and he received his master's and PhD degrees from MIT, 97 and 2002, where he also continued as a postdoctoral associate for the Department of Mechanical Engineering until 2003. Before joining the University of Utah, and from 2003 to 2004, he was an assistant professor in the Department of Mechanical Engineering at North Dakota State University. Ourselves here at Quanser are very proud to have been working and collaborating with Dr. Mascaro for many years. And honestly, you know you are dealing with a savvy and demanding researcher when none of the Quanser devices that he uses in his lab are off the shelf and standard. Every Quanser solution he uses is pretty much customized to some degree, and that's because he wanted it customized. He made it custom. He made us customize it for him, and he's even gone ahead to customize some of our devices himself, some of which you might see in the presentation today. We're extremely happy to have been part of this and to have been the reason that this was possible. But now I'll stop talking and I'll pass it on over from Toronto all the way to Salt Lake City. And without any further ado, it's my extreme pleasure to introduce our presenter, Dr. Steven Mascaro. Steve, over to you.
Okay, I'm excited to share with you all what I've been doing with Quanser over the past decade or so. So to put this all into context, we have a robotics track at the University of Utah where we offer masters and PhDs in robotics. And so I came to Utah to be part of this robotics track. And we have a couple of gateway classes that we teach intro to robotics in the first semester, which is mainly kinematics and manipulators. And then in the second semester, we teach our students intro to robot control, which is my course that I've developed here and been developing over the last decade. And then both of these classes act as a gateway into our electives in the robotics track in various areas. So in terms of hands-on control education, what I was originally looking for when I developed my robot control class was a serial robot manipulator that is affordable, open architecture, safe for students to work with, has at least 2 degrees of freedom, so that we're able to showcase various forms of model-based nonlinear compensation and force control. And so there really wasn't anything out there, any device that satisfied all of this criteria, to my satisfaction at least. You know, on the one end of the spectrum, you can, make a do-it-yourself device like the haptic paddle for under $100. It only has 1 degree of freedom though, and so it's kind of a limited use in teaching students some of the more advanced concepts of robot control, controlling multi-degree of freedom systems, compensating for nonlinear dynamics. And then on the other end of the spectrum, you could buy something like the Sawyer robot from Rethink Robotics for $22K. It has lots of degrees of freedom and is able to showcase all kinds of methods of advanced robot control. But it's almost too complicated of a starting point for the students to be able to control 7 degrees of freedom. So I really wanted something kind of in between this. And so that's where Quanser came in. So I approached Quanser over a decade ago now. And they offer a very nice suite of products, including their SRVO2 servo motor modules. And so in partnership with their engineers, we designed a new add-on for their modules that actually allowed us to put 2 of these modules together to form a 2 degree of freedom serial robot manipulator like you see in the picture here. And so this is what we use in our robot control class now. And it's nice because since the units are all modular, we can take them apart. We can start by having the students learn to control 1 degree freedom modules. We do that in our classical control class as well as our state space control class. We have various of Quanser's other add-ons such as the inverted pendulum add-on and flexible ling and flexible joint add-ons for these modules. But then when it comes time to use these in my robot control class, we put them together with the 2DOF add-on and form these 2 degree of freedom manipulators, which are just complex enough to demonstrate some of the nonlinear model-based compensation techniques, but not too complex. Makes a good starting point for the students. They're very safe to use. They're incapable of harming anybody. The current to the motors is strictly limited to 1 amp of current, so they can't really have enough torque to hurt anybody. And the other nice thing about these robots is by mounting both of the motors on the base on the table, you avoid carrying the weight of the second motor on the links themselves. So we can use nice lightweight links and get nice high-speed motion out of these linkages while keeping the heavy motor stations on the base of the robot. And so it kind of makes for some interesting kinematics. I won't spend too much time on the kinematics here, but you can see here on the left, motor number 1 is directly driving link number 1 of the robot. And so we then have a gear system on that and an encoder that's directly measuring the joint angle of link 1. And then on the right-hand side, we have motor number 2, which also has a gear system, but then has a pulley to transmit the motion to link number 2. So motor number 2 is driving link number 2 through that pulley system, allowing motor number 2 to keep its weight on the table rather than on link number 1. And again, encoder number 2 is positioned such that on the near side of the pulley system, it's actually measuring the absolute angle of link number 2, which turns out to be convenient, as I'll show you in a minute. Again, I won't spend too much time on these kinematics, but this is the first step in presenting the math to our students. We show them how you can relate the position of the end effector of this robot, XY, to the joint angles, theta 1 and theta 2. And so here in this figure, theta 1 and theta 2, those are the relative joint angles between the 2 links. You can see how those are related to phi 1 and phi 2, the absolute joint angles of the 2 links. And the 2 are related between each other via what we call the transmission kinematics. So there's a matrix that relates the relative joint angles thetas to the encoder angles phi, which happen to coincide with the absolute joint angles of the robot through this matrix, which we call the pulley Jacobian, which contains ratios of pulley diameters. And in our situation, the pulley diameters are equal to each other, so everything simplifies to a very simple pulley Jacobian, which again, in this case, means that what our encoders are measuring corresponds to the absolute joint angles of the robots with respect to the base frame of the robot. And we also emphasize with our students the duality of this Jacobian. So the Jacobian for this robot not only relates the velocities of the joints to the velocity of the end effector, but it also relates the torques between the joints and the forces at the end effector. And this is going to come in really useful when we do various kinds of force control. And so we can actually compound our manipulator Jacobian J with our pulley Jacobian JP to form one big compound Jacobian that maps directly from our encoder angles, what we're measuring, to the end effector or operational space or task space velocities of the robot. And then that same Jacobian, compound Jacobian transpose is what relates the forces at the end effector to the joint torques. We also teach the students about the dynamics of this robot. So this is really key because all of our controllers are going to be based on the dynamics of the robot and compensating for the various nonlinear terms that you find in the dynamics of the robot. So the equation here shows the standard form of a robot dynamics. So this could apply to any manipulator arm. So we have an array of torques that we send to the motors on the left, and then that's balanced out by the inertia of the robot, the velocity-based terms, which include centripetal and Coriolis torques, and then the gravity terms, which are functions of the joint angles. And for this 2-degree freedom robot, we end up with matrix equations with 2 rows. So we have torques on both joints, tau 1 and tau 2. We have a 2x2 inertia matrix. We have all those centripetal and Coriolis terms, which are functions of velocity squared, and then our gravity terms. And the interesting thing about this robot, the way we've configured the kinematics with that pulley system, is that when you actually convert from relative joint angles theta to the absolute joint angles, which is what we're measuring with the encoders, the Coriolis torque actually disappears. Some of you may know the Coriolis torque is just an artifact of using a relative coordinate system. And so when we abandon those relative joint angles, those go away. And so here's what our final dynamics of the robot look like. So on the left-hand side, we have gear ratios N1 and N2 times motor torque constants, KT1 and KT2, times the current. So we're actually controlling the current to our motors. So in addition to these 2 DOF robots from Quanser, we also have some of Quanser's AMPAC amplifiers that are capable of sending controlled current to each of the motors. And we do it that way because by controlling the current to the motors, we can make sure that we're not sending too much current. We can keep our motors from burning out. And then also we don't have to worry about back EMF terms appearing in our dynamics when we control the current. So anyway, on the left-hand side of the equation, we're inputting current. And then on the right-hand side, we have all the torques again, the inertia torques, the centripetal torques, Coriolis torques have gone away, gravity, and then we can also add in some frictional torques. And so for this Quanser robot, we've relied on Quanser to provide us with the mass parameters of all the links of the robots. And then we've experimentally identified some of the friction and damping parameters. So we have good values for all of the numbers that go into the dynamic equation here. And therefore we can use that knowledge to compensate for all the nonlinearities of the robot as we teach the students how to control the robot. So in teaching the students how to control the robot, we do it both in simulation and in real time on the real hardware. This is one of the nice things about being able to use MATLAB and Quanser's Quark software. So we have MATLAB, we have Simulink, and we have Quark installed from Quanser. And then in addition to that, I put together a custom graphical user interface, which I programmed in MATLAB, that allows the students to visualize the motion of the robot. And the way this works is the graphical user interface actually places an event listener inside of the Simulink model on one of the scope blocks. I'll show you in a second. So as the Simulink model is running and sending data to a scope block, that data is then sent over to my graphical user interface, which then uses those joint angles to plot the configuration of the robot. And so we can do this in simulation, or we can do it in real time on the real hardware. And so let me close out my PowerPoint presentation for a moment and switch over to MATLAB and show you how this works. So here's an example of one of our most simple Simulink models here, where the students start out with basic PD control on both joints of the robot. So this is basic decentralized control. We're not doing any model-based compensation right here. And I've got this blue block in my Simulink model that's simulating the dynamics of the robot manipulator. And if we look inside of there, we've got the forward dynamics of the robot programmed in as an embedded MATLAB function. And so you can see here, I've got all of those mass and friction parameters of the robot plugged in here with the actual values that we've experimentally identified. And then we can form our gravity matrix, our friction matrix, our centripetal matrix, our inertia matrix, and we put this all together and basically simulate the actual dynamics of a real robot, okay, based on the parameters as closely identified as possible, okay. And then so we've got this blue block outputting phi, our encoder angles, as if we were actually measuring those. We compare them to a desired trajectory. So I've got a trajectory generator here, which is generating a circling trajectory in operational space for the robot. So we're essentially telling the robot to draw a circle in space as best as it can. We pass those through the inverse kinematics of the robot, which creates a desired trajectory in joint space or in encoder space. We form an error in joint angles and then penalize that with a PD controller, and we're all set to go. And so at this point, you can just hit the play button on this Simulink model and run it as is, or you can run it through my graphical user interface here. So we type in the name of my model here, for example, we hit load, and then I can change the speed of the trajectory. That'll poke in different values into my Simulink model, and then I can hit the start button, and it commands my Simulink model to start running. And here we can visualize the motion of the simulated robot trying to draw a circle, again, in task space or operational space. And so this is a relatively slow trajectory. And so you can see that at slow speed, the robot does a pretty decent job of drawing the circle and tracking the desired trajectory. But if I stop this and speed up my circle to 1 circle per second, now you can see the robot's going to have a harder time dealing with the nonlinear torques created by the inertia coupling, the centripetal torques, the frictional torques. So the circle is kind of egg-shaped because of those nonlinear dynamics. And so what the students find out is that using PD control alone is not enough to do good trajectory tracking at high speed. We could try to increase our PD gains even further, but then you end up saturating the amplifier. You can't deliver enough torque to the motor. And so the message moving forward is that we need to learn to compensate for these various nonlinear dynamics, for the inertia coupling, for the centripetal and Coriolis stuff, in order to get good trajectory tracking at high speed. Let me return to my PowerPoint presentation. And once the students do that in simulation, they can do the same thing on the real robot hardware. So they would just replace that blue block in my Simulink model with input and output blocks that talk to the encoders and motors, and they can run the exact same controller on the real hardware and see how does the performance in real life on the real hardware compare to what we saw in simulation. And so here's some videos of the controllers running on the real robots. So on the left, you see the 2DOF robot drawing a circle at low speed. And then if I start the video on the right, we'll see the robot drawing that same circling trajectory in high speed. All right, So again, the great thing about this is the students can try their controller first in simulation, make sure that it works in simulation, then they can take that exact same controller, swap out the blue block for the hardware input and output block, and try that exact same controller on the hardware with the exact same values and see how it works in real life. So I'll show you quickly some of the different controllers that we teach the students. So again, here, this is the one that I showed you a moment ago in Simulink, simple decentralized PD control. So there's no model-based compensation at all here. Each joint is penalized with a proportional and derivative gain, and sort of each joint is doing its own thing without regard to what the other joints are doing. And so yes, the robot can draw a circle, but it doesn't do very well at high speed. So here's an example. It shows a plot of the actual trajectory over top of the desired trajectory, and we can plot the joint errors versus time. And so the students can compare the performance both at low speed and at high speed. So we can see at high speed, the trajectory becomes even worse due to those nonlinear dynamics. And so then we go through a progression of different tracking controllers. So we next try computed torque feed-forward control, where we have a complete model of the robot dynamics and use that to compensate for everything. Then we have inverse dynamics control. We try robust sliding mode control. We try adaptive control. We even try learning control. So I'll move through these rather briefly just to give you a quick picture of some of the different controllers we use. This is computed torque feed-forward control. So this block down here at the bottom where it says feed-forward compensation, contains a complete model of all the dynamics of the robot, all those inertia parameters, friction parameters, gravity parameters. And so we're basically using the desired trajectory of the robot to calculate at each instant in time how much torque do each of the robots need to compensate for all of those dynamic effects. And then we feed that forward to our manipulator. Okay, and so that works much better than PD control alone, but it's still not really decoupling the dynamics for us. If you recall back on that slide where I showed the dynamics of the robot, the inertia matrix is coupled, right? So a torque on one joint creates motion on another joint and vice versa. And so in order to do the best control, we really need something that can decouple that inertia matrix so that if there's an error on one joint, I can send torques to both joints in the right proportion in order to reduce that error. And so that's what inverse dynamics control does for us. So this is the next step in teaching the students. We have some feedback compensation in this case that cancels out gravity and centripetal torques. But then we take our inertia matrix and we place it in series with our PD gains here. And this actually decouples the influence of the PD gains on the robots. So by multiplying the PD gains by the inertia matrix of the robot, which is coupled, that then distributes torques to both motors of the robot in just the right proportion to take care of error on either of the joints. And so this is what we call centralized control, right? So now, rather than each joint doing its own thing, now we have one centralized controller that's sending torques to both motors in just the right proportion to handle the errors. Then we can try robust control. So we have the same inverse dynamics control down here, but then we pick off our tracking error and create a sliding surface up here. Some of you may be familiar with sliding mode control. And so it's kind of like a bang-bang controller that hits your motors as hard as you can in one direction or the other, depending on the sign of the error. And so adding in the sliding mode action, so the torque from the sliding mode controller comes down here and adds in with the effort from our PD controller. And so the students find that this works really great in making your controller robust against modeling error. So now they can go in and intentionally alter some of the mass parameters in this blue block or some of the friction parameters, pretend that they don't have an accurate model of the robot, and see how well does this robust controller compensate for that. And so this shows a comparison as you go through this progression of controllers at high speed. So on the left, we have just PD control. It's not doing a very good job of tracking the circle. With computed torque feed-forward control, it does a little better. With inverse dynamics control, it does even better. And then with the sliding mode control, it does the best of all. And so the students can see that the joint errors decrease as we progress, as we progressively find better ways to compensate for the nonlinear dynamics of the robot. And then we can also do adaptive control. So this would be a scenario where we're pretty confident that we have the dynamic equations correct for the robot, but what if we didn't know the values of all those mass parameters? So we can teach the robot to adaptively learn what those mass parameters are. And so when we implement adaptive control, the robot will start circling, and with each circle, it'll get progressively better as it's adapting to the unknown mass parameters of the robot. And in the middle plot, you can see the joint errors getting progressively better. And then on the right-hand plot, you can see those unknown mass parameters are converging to some steady state value. And it's interesting for those of you that know adaptive control, you know that the tracking error is supposed to converge to 0 theoretically. Of course, it doesn't in practice. But the parameter errors are not guaranteed to converge to their true values. They just converge to something that guarantees good tracking error. So it's a fun learning experience for the students. They try each of these controllers out in simulation first, and then they try them on the real robot hardware. And of course, nothing works as well on the real hardware as it does in simulation. And that's the real value of having a hands-on education like this, is they can see what really works on the real robots. So just in summary for that section, the learning outcomes are students learn that higher PD gains result in better tracking, but too much results in amplifier saturation. And so you need, again, this model-based compensation, especially at high speeds, in order to get good tracking error without saturating your motors. The students can see the trade-offs between doing feedback and feed-forward compensation. They can see the benefit of both linearizing and decoupling the dynamics of these robots. And then they can experiment with different ways of dealing with model uncertainties, such as sliding mode control versus adaptive control. Okay, so what's even more exciting, so we spend the first half of the course basically doing these various types of motion control. And then in the second half of the course, we do various kinds of force control. And in order to do force control, we basically came up with a way of making our own 2-degree of freedom force sensor on the cheap that we could add to the end effector of our Quanser robot, as you see here. So with a zoomed in view, this is a do-it-yourself, low-cost 2-degree freedom force sensor. So we purchased some thin beam load cells from Omega. They're under $100 each, and 3D printed some parts to hold those. And so we've got them, the two thin beam load cells, oriented orthogonally to each other, so I can measure forces in both the X and Y direction of the robot as it moves in the plane. And then, of course, a reminder that if we measure these forces, Fx and Fy, that the robot is pushing on the environment, or the environment is pushing on the robot, depending on how you look at it, then we can use our transpose of our Jacobian to map those back to equivalent torques at the joints of the robot in order to be able to compensate or apply the required torques to match the force. Our graphical user interface has a feature where it can display a wall in the environment. So this is a horizontal wall, aka the tabletop. When we do this in practice on the real robots, we'll have the force sensor on the robot, and it'll be pushing on the tabletop, on the bench top in the laboratory. We can simulate that in our graphical user interface and try different types of force control. So before we introduce force control, we teach the students about how to switch your controller from joint space to operational space, right? So all the controllers I showed before in joint space, we're generating a desired trajectory. We're using the inverse kinematics to put that in terms of the joint angles, and then we feed back our joint angles. We create an error in the joint angles and penalize that with PD gains, right? So our penalty is occurring in joint space. The trade-off, or sorry, the alternative is to do this all in operational space or task space. So here, we generate our trajectory in XY coordinates for the end effector, but now we don't need the inverse kinematics anymore. We form an error in operational space in terms of the error in the position of the end effector. We penalize that with a set of PD gains. And so that creates kind of like a penalty force in task space. And then we use the Jacobian transpose to map that back to an appropriate penalty in terms of joint torques, which you can then send to our robot manipulator. And then, of course, we need the forward kinematics in the loop so that we can take our encoder angles phi and calculate the position of our end effector to feed back and compare it to our desired position, right? So this is an operational space controller where we have the Jacobian in the loop. And so the students, again, appreciate the utility of knowing the Jacobian. In this case, the compound Jacobian, we've got to include the pulley Jacobian in there to properly map between operational space and joint space. And then we do a progression of different force controllers. So starting with this PD control in operational space, we can teach the students to do what I call stiffness control, which basically means you just intentionally lower the PD gains in certain directions. So for example, if I want the robot to be pushing against the tabletop and not exert too much force, right? We don't want to damage the robot or the force sensors. I can lower my PD gains in the Y direction, the vertical direction, to mitigate the force against the tabletop. And so those PD gains kind of act like a virtual stiffness and damping on the robot. And then we can actually upgrade that to full impedance control, where we can actually specify a desired stiffness, mass, and damping in both the X and Y directions for the robot to behave like. We then teach the students compliance and admittance control, which are very similar, but the causality is flipped. I'll talk about that in a second. We teach the students hybrid position force control, and then we can actually do stuff with multiple robots. So we try some multi-arm coordination using 2 robots and some master-slave teleoperation using 2 robots. So here's an example of what happens with stiffness control. So if I take that PD control in operational space and lower my PD gains in the Y direction, then when the robot comes into contact with the tabletop, it reduces the contact force. So the robot's actually trying to do a circle still, but then it hits the tabletop. And so it's forced to only do a hemicircle trajectory when it is really wanting to do the full circle trajectory. And so this entire direction where it's cutting across the circle here, that's when it's in contact with the tabletop. And so we can plot the forces versus time over here. You see you get an initial impact force when the robot first hits the wall. And then the force kind of ramps up and back down again as the robot gets to the other side of the circle. And so by reducing the stiffness, by reducing the PD gains in the Y direction, we can keep the force to within 2 newtons, for example, on this particular scenario. But that initial impact force we can't do anything about by lowering the PD gains only. That's when we need to actually move to full impedance control. So with full impedance control, we actually put the inertia matrix back in here. It's kind of like inverse dynamics control. And then in order to control the inertia of the robot, technically you would need to feed back acceleration, but we don't like to do that because we don't have an acceleration sensor, and we don't want to double differentiate position signal, which leads to noise. So instead we cheat by sort of feeding back force as a measure of acceleration, and then we can divide that by our desired mass matrix. So right here, this 20 means that I'm trying to reduce the effective mass of the robot by a factor of 20 in the Y direction. So we're taking this, heavy, in quotes, robot and making it behave like it's much lighter than it really is. And so when we do that, we can see that we can get rid of that impact force, right? So now it's as if the robot virtually has much less inertia than it did. And so when it hits the wall, that impact force no longer creates a big spike. We can do something similar with admittance control. Here the causality is flipped. So we're taking force feedback from the robot, putting it through a compliance or an admittance transfer function, and using that to alter the desired trajectory of the robot in a mass spring damper-like behavior. And then you can control the mass, stiffness, and damping by picking the parameters in this transfer function down here. So you can see in this case, I've got a Y admittance, so I'm making the robot behave like a mass of 1, a damping of 10, and a stiffness of 25 in the vertical direction. And then there's 0 admittance in the horizontal direction, since we want the robot to keep doing good tracking in the X direction, but be sensitive to the force in the Y direction. And so we can feed that back and essentially alter our desired trajectory in response to the force from the force sensor. But then the benefit of admittance control is I can keep my PD gains over here very high, so I still get really good trajectory tracking when the robot is not in contact with the wall. But then when the robot is in contact with the wall, it's very sensitive to that force according to the admittance parameters that I define. The only downside of admittance control is the students find that it's much less stable than impedance control. Because of this admittance transfer function, we're adding a couple extra poles to the dynamics of our system. That makes this system more prone to going unstable, especially when you're in contact with a relatively stiff wall. The wall stiffness kind of acts as part of the root locus gain in the system. So a stiff wall drives the system unstable for admittance control. So similar performance with the admittance controller, only much better trajectory tracking than impedance control. But like I said, it has stability issues when the environment's stiff. And then we move to hybrid position force control. This is where you want to control position in some axes, but force in other axes. So again, picture the robot stroking the tabletop. What if we want to actually control the force against the tabletop to some desired level while stroking back and forth in the X direction? And so that's what this does. So we kind of have on the upper half here a position controller. So we have our position trajectory, which is still generating a sinusoidal trajectory back and forth in the X direction for the robot. And then on the bottom half, we have the force controller. So we specify a desired force right here of -2 in the Y direction. So we're basically telling the robot, push down on the table with a constant force of -2 newtons while you're stroking in the X direction. And so we penalize both the position error and the force error. And then we pass those through a pair of selection matrices, which basically says only do position control in the X direction, only do force control in the Y direction, then add those two control efforts together here at this big central summing junction. And then over here, we've got inverse dynamics control again, which is decoupling the dynamics of the robot so we get good performance. So the students can try that as well, again, both in simulation and on the real robots. Then the students can monitor the forces versus time. They can see how, for example, on the left, without any integral action on their force controller, it can't quite get to the desired force of -2 newtons. With the integral action on the force controller, they can get exactly the 2 newtons of desired force that they want. Here's some videos. So on the left, you can see the stiffness controller. So the robot's trying to draw a circle, but the circle brings the robot into contact with the tabletop. And so by making the robot compliant in the vertical direction, that mitigates the contact forces that occur when it hits the tabletop. On the right-hand side, we have a video of hybrid position force control. So in this case, the robot is stroking back and forth on the tabletop. And so it's trying to keep that force against the table to a constant 2 newtons while stroking back and forth. And then of course, in practice, with the real robots, we've got friction coming into the picture. And so the students can see, okay, In simulation, the hybrid controller did great, but now in practice, when we've got all this friction present, how is the hybrid controller actually doing? I'll skip this since we're running low on time. We can also do teleoperation with a pair of these 2DOF robots. So one can be the master, one can be the slave. So we can do this both in joint space and in operational space. So when I grab the master and move it, the slave robot is basically replicating the joint angles of the master robot. Or then on the right-hand side, we do the same thing in operational space, only now we're just telling the slave robot to follow the end effector position of the first robot. And so the fun thing is when you do this in operational space, you can, if you bring the robot to its singularity, you can get the slave robot to toggle between its elbow up and elbow down position. And the operational space controller doesn't care whether the robot's in elbow up or elbow down as long as the two end effector positions are still matching. And then we can also do multi-arm coordination. So I'm going to click on a YouTube video here. So this was a special project that some of my students did at the end of the semester. They got 2 of the robots to cooperatively work together to carry an egg. So we implement this multi-arm coordination as kind of a form of hybrid position force control. So by formulating a special task space, you can get the 2 robots to share the burden of both controlling the position and the forces on the egg. So that's kind of fun for the students to do. And then finally, our very last experiment of the semester is visual servoing. We teach the students how to implement visual servoing. So we actually mount a video camera on the end effector of our 2DOF robots, and we can get it to track a dot on a piece of paper using a couple different kinds of visual servoing. And then on the right-hand side, we can even get one robot, a master robot, to track the slave robot using visual servoing. And so I promise here, I'm not cheating. The 2 robots aren't talking to each other. One robot is simply moving the dot, and then the other robot is tracking it with the little fleet camera mounted on the end effector. So lots of fun things for the students to do. So position control, various forms of position control take us through the first half of the semester. Then all of these force and interaction controllers take us through the second half of the semester, and we're done. And so just to summarize, we've developed this 2DOF robotic platform. It's modular. You can take it apart. You can use it with different Quanser add-ons. It's open architecture. This is really important. We can directly control the torques on the motors to compensate for all of these nonlinear dynamics and various kinds of force control. It's safe to use. It's not capable of hurting anybody. And it has just enough degrees of freedom to demonstrate the key robot control principles, such as compensating for nonlinear dynamics, using the kinematics and the Jacobian in the loop to map between joint space and operational space. And working on operational space makes it convenient to try all these different kinds of force control and teleoperation and multi-robot coordination. So I'm going to stop here and open it up for questions.
Thank you very much, Steve, for a fantastic presentation. Very, very interesting stuff, especially the simulations of your visual simulations, comparing it to the reality was very interesting. We do have quite a few questions. Some are focused on the technicality and the different types of control algorithms that you use, but there's also a few on the course itself and the nature of the course and its prerequisites. So let's try to get as many as possible, and encourage people to continue sending their questions. But the first one, let's start with one about the controller. And the question is, what are the advantages of using a PD controller, and why not use a PID?
Well, PID will work fine if your robot is moving very, very slowly, right? But once you start moving quickly, such as these rapid circling trajectories, then the integral controller just can't keep up. and you find that sliding mode controller, for example, does a much better job of adding robustness than adding an integrator.
Thank you so much. The next question is asking, you spoke about identifying the friction parameters. Can you say a little bit further about the ways or the techniques you follow to evaluate such parameters?
Yeah, so identifying the friction accurately is actually the most difficult thing to do in terms of identifying the parameters. It's actually been some time since I did that experiment. I'm trying to remember back. Yeah, we basically empirically determined those. So we model both a viscous component of friction proportional to velocity, and then we model a static component of friction where we basically just use the SGN function. So the friction is just a constant, but flips its sign depending on the direction of the velocity. And so it's been too long ago. I don't remember the exact experiments we did to identify those, but we identified both the viscous damping constant and the Coulomb constant to the best of our abilities. And that's one of the biggest differences that you see, so in the simulation, we pretend that we have a perfect model of friction, and then of course the robot does great when we compensate for it. When we do this on the real robots, then we see that our friction model is far from perfect, and really it takes that robust sliding mode control, does the best job of compensating for the static friction.
Thank you very much. The next question is about force estimates. How do you calculate or estimate the forces, the contact forces that are being applied to the system?
So when we do this in simulation, well, I can actually show you. Since you asked, here's a simulation of the two robots working together to carry an object. And if I look in the Simulink model here, in my blue block, it's now changed from a robot dynamics block to a robot environment block. And so in here, I have a block called block dynamics. And so I'm basically programming the block, in this case, the environment, to act like a spring. And so it then simulates forces based on a spring law for the environment. It does the same thing when I've got a wall in the environment. It's approximating the wall as a virtual spring where I can set the stiffness. And so then it generates these virtual forces, which I can feed back and use for simulating my force control. Of course, when we do this on the real robots, then I actually have that 2DOF force sensor on the robots, which are actually measuring the force in the X direction and the force in the Y direction. And then I can use, so of course that's in the frame of the end effector of the robot. I can use a rotation matrix to rotate those into the base frame, and then use that in my various forms of force control.
Thank you so much. One more, in the visual servoing example, what type of controller was being used there?
Yeah, so that was an image-based visual servoing. So Quanser has these handy blocks that work with the point gray research cameras, so they have a block that will process an image for you. Well, they have a block that'll capture an image from the camera for you, a block that'll process that image and output the XY coordinates of the dot in the image. And so then we can use those XY coordinates of the dot as features for image-based visual servoing. So I can specify my desired feature values are basically the pixel coordinates of the center of my image, right? So I desire for the dot to be in the center of the image. I compare that to the actual XY coordinates and then put a penalty on that. And then I have to create an image Jacobian that maps between feature space and joint space of my robot. And so the controller looks very similar to my force controllers, only instead of penalizing the force and using the manipulator Jacobian, in this case, I'm penalizing the image features and using an image Jacobian.
Okay, the next question might have something to do with the days and the times that we're living in, but the question is, have you ever thought to try an online web version or a configuration of this, either with real-time connection to the real robot or to a virtual model of it?
Well, yeah, because of our quarantine situation, I considered that. They shut. I was actually in the middle of teaching this class this spring, and they shut us down a couple weeks ago, like everybody else. And it's very unfortunate because now the students can't do this on the real hardware. They can do this on their home computers. They can do the simulations because most of my students have MATLAB, and you don't need Quark just to run the simulated versions. You only need Quark to run it on the real robots. But I thought to myself, could I set up some kind of remote access so the students could somehow control the real robots virtually through the internet? It would, I guess, be possible, maybe just having them take control of the screens on our lab computers, and having, you know, MATLAB and Quark on the lab computers. But the problem there is they'd still need somebody to be in the lab to have their hands on the robot, because prior to running each controller, you have to put the robot in its home position, because these encoders are just relative encoders, so you always have to start the real robots in their home position. And so for a large class of 30-some students, we decided it wasn't practical to do that this semester at least. But in theory, it'd be possible as long as you have somebody there in the lab to home the robot for you every time.
Right. Of course, these are all the challenges that are being highlighted more and more these days. Every campus and everybody has tried to come up with their own short-term solution of this just to get by these days. But of course, it also opens the conversation into how this can be expanded, scaled in the future, and actually used in a proper way. Many conversations around that these days. So just a couple of last questions now, more focused on the nature of the course, because it does seem like such an interesting course. First of all, there's a question about the prerequisites of the course. It seems like there are a lot of material to cover in one course. So first of all, is it a semester-based or an annual course, and what are the prerequisites?
Yeah, so it's a one-semester course. The prerequisites, as you can see on my slide here, are in the first semester, the students take a course in robot kinematics, so they've already had that foundation, and they actually cover robot dynamics at the very end of that course as well. But I usually have to review robot dynamics in the first week or two of my class. A second prerequisite is some kind of class in linear control systems. So we assume the students have had some exposure to PD control and block diagrams and root locus techniques. And everything else we cover ourselves. And so I'm basically spending one 80-minute lecture on each of these different types of controllers, right? So I'll spend a lecture on feed-forward control, a lecture on inverse dynamics control, a lecture on robust control, a lecture on adaptive control. And so I don't have time to go into super depth on the theory of all of those things, but I give the students just enough information to know how to implement each of those different controllers and to kind of have an intuitive understanding for what it does. And then they can go on and we have many other advanced control classes in our department that the students can go on and take if they want to have a whole semester on nonlinear control, for example.
Got it. Another interesting question, which I think goes back to your sampling time. How much is your solver time normally used in both the simulations and also real-time runs?
Yeah, so we, on the real-time robots, we of course have to use a fixed sample time. Quanser recommends about a 2 millisecond sample time. We found we can get away with a 1 millisecond sampling time on most of these controllers. Anything smaller and Quark can't handle that. But that's sufficient to do very smooth control on the real-time robots. When we do this in simulation, you can pick any sample time you want, or you can let MATLAB have a variable sample time and it can determine whatever sample time it wants. but we do encourage the students to stick with that same fixed sample time of 1 or 2 milliseconds, even in simulation, just so that when they port their controller from simulation to the real hardware, they can expect similar behavior.
Got it. And maybe we can take this one as the last question since we're approaching the top of the hour. You spoke about a Simulink block in which you have the dynamic model of the robot implemented, and then eventually you replace it with the actual connection to the hardware. When students go through that and switch from simulation to model, I guess people basically want to know how good your model is. Do they see any difference? And if so, what they are? Have you left them in intentionally, or are they actually things that you haven't been able to model?
Yeah, so there's a big difference in tracking performance when you move from simulation to the real robots. And that's to be expected, right? Because in simulation, we're using a perfect model, and so we perfectly cancel out all of those gravity and inertia and Coriolis centripetal stuff. But our model is far from perfect. And so all of these controllers, the tracking error is much larger when you try it on the real robot versus in simulation. But in a relative sense, you can still see the same progression, right? So even in experiment, the inverse dynamics control will do better than feed-forward control. The robust control will do even better yet.
Okay, thank you very much, Steve, for the presentation and for the Q&A. Thanks, everybody, for attending. And with that, I'll pass it back to my colleague, Susanna, for the closing comments.
Yeah, thank you. Thank you, Pasha. Thanks, Stephen, for the great presentation. Thanks to all our attendees for joining us today and for asking great questions. This webinar was recorded, as I mentioned, so you will receive a link with the presentation, and you can revisit it or share it with your colleagues if you think they would be interested. I would also invite you to look at our previous user webinars. As you can see, we had run quite a few talking about our software, our different solutions from shake tables and drones. So it's quite an interesting collection. And if you have time, I'm really sure you would you will find those interesting. Thanks again for today's participation. Stay healthy and safe wherever you are, and we are looking forward to see you in person, hopefully soon at a conference or during a visit. Thanks again, and have a good day.